All right. Thank you, everyone, for attending. I want to talk to you today about overlooked, ignored, and denied physics. I'm also of the opinion that physics has got lost in too much abstractions. When I was studying physics, I liked all of the theories on the stuff. I found it very fascinating. But in the end, overall, I couldn't make sense of it. There were so many open questions and it was so confusing. And this is why I also started out doing my own research and reading literature from other people. And in the end, I think we should take a step back, like some of the others have also recommended, and start collecting clues so that we can make inferences from the clues that we find. I think a lot of the clues that I will be presenting today, many of you have never seen before, so I hope so, that I'm not overstating. But I also must add that I do not have a fully consistent theory. So I've collected lots of parts, I tried to put them together as good as I can, but it's not a fully consistent theory. Okay, so let's jump in now. First, I want to start just with a slide about the symbols that I use. Most of them are pretty standard. A few things are worth pointing out, though. Everything that's related to the Planck units has a subscript L. Everything that is related to the Compton wavelengths has a subscript C. What definitely comes up a lot is the reduced Compton wavelengths, which is just the Compton wavelengths divided by 2 pi, and also the Compton frequency associated with the Compton wavelengths. Please do not confuse the symbols for the hydrogen radius and the Hubble radius. Yeah, pretty similar. And I also stated the value for the Hubble constant that I use explicitly because there is still some uncertainty about what is like the correct value. The starting point of my presentation is the Compton wavelengths and the claim that the Compton wavelengths is a real geometric property. It is not just some intangible quantum physical property with no real meaning in 3D space. I think this is a very, very crucial thing. If you have a new theory and you cannot incorporate the quantum wavelengths in a real geometric sense, then there is something missing, in my view. And as you will see, this will go a long way. A lot follows from, we're following that trail. A lot of things will follow from that. Okay, so in particular, this means that the Compton wavelengths defines the circumference of a spin-1/2 particle. This is where we'll start. This also implies that the radius of a spin-1/2 particle is the reduced Compton wavelengths. And when I talk about a spin-1/2 particle, in particular, I mean standalone fermions. I'm just talking about electrons, protons, neutrons, etc. Okay, this slide now shows the first clues for the claims that I made. The first thing is that if you look at the experimental proton radius, it is pretty much 4 times the reduced Compton wavelengths of the proton. I think this is pretty much ignored. And the fact that we're having an integer number and not just some weird arbitrary factor is already the first clue that there's the Compton wavelengths have a real geometric meaning. Next thing is, we can calculate the electron's magnetic moment in a classical way. We just have to have a coil which has the size that I presumed for the electron that we're talking about the radius of spin-1/2 particles. If you just take the area and also take the associated current, so you have the fundamental charge circulating around that circle, in the coil with light speed, and you get this frequency. So you have a current E times the Compton frequency of the electron. And you just multiply it all together, and somehow you get the electron's magnetic moment. I think this is a pretty astounding coincidence. And you do not even need a fudge factor like the gyromagnetic ratio. So I find that pretty astounding. And also the third clue is that the hydrogen radius and the reduced Compton wavelengths of the electron, they are also related by a factor of alpha. And since the hydrogen radius is definitely something real and measurable, the reduced Compton wavelength also has to be, because why would that be something real and that would be just something imaginary? Doesn't make sense to me.
Sorry to interrupt, but just when it says equal, you mean approximately equal, right? To what sort of accuracy?
Here or here?
Everywhere.
This should be pretty accurate. I mean, maybe there are some digits, like the fifth, sixth digit, some quantum effects missing, but that's accurate in standard physics. There might be some quantum mechanical effects that are not considered, but that is very, very accurate.
For all of these equal signs?
Yeah.
Cool.
Yeah. So here it is like two digits. Like this is 4.00. The third digit, then it's getting so. Yeah, but it's pretty accurate. And this is like really equal.
Mark, are you saying for the electron's magnetic moment, you're using a classical calculation where you have
Yeah. This is the classical calculation.
electron
Just
in orbit?
yeah, electron in orbit. Yeah, or the charge being distributed. The charge being distributed, actually, around the complete coil. The fundamental charge would be like distributed out equally.
So the charge is spread out.
Yeah, and then it's like rotating with light speed.
The coil's in a circle.
Yeah. And the size of the circle is exactly like the electron size, like it was like given here. That would be the radius. So I find that pretty amazing. So, and this slide shows how it's possible to create a simplistic particle model that tries to incorporate the findings of the previous slide. The physical reality might be more complicated, so I'm not saying it's really a sphere, but at least it appears to be a sphere. So what we have is a spin 1/2 particle appears to be a sphere that is rotating with light speed around the equator, and it has superimposed flow dynamics. And these flow dynamics have a symmetry. And this symmetry leads to the funny fact that for calculations, you do not really use the sphere, but you use a disk, because kind of the symmetry, components cancel out, and the actual geometry that you should use is that of a disk. And this is again why when I was talking about the electron's magnetic moment and the coil, this is where that comes from, because due to the symmetry, it's actually reduced to the geometry of a thin disk. And this also leads to the funny fact that you can now calculate particle spin through just ordinary angular momentum, which I was always told is not possible, but you can do it with I will ask more questions later, because I have some.
The speed of light speed, is it corrected with fine structure constant?
No, this one is just light speed. No, yeah. So at the equator, it's light speed. And there is superimposed flow patterns. The flow patterns are more complicated. I have not perfect equations for the flow patterns, but we'll get back to that on later slides. And there is also another angular momentum component. So though the spin axis has h bar half, it's a typical spin. But according to Randall Mills, who is working with a similar model, there is also another angular momentum component of any axis that lies in this plane. And that would have an angular momentum of h bar divided by 4. And with that additional angular momentum component, it should be explainable, according to Randall Mills, to also explain the Stern-Gerlach experiment of quantum physics in a classical way. So that's the next very interesting thing. And moreover, spin and magnetic moment are linked very naturally in this simple model. Okay, the next interesting set of coincidences with the simple particle model and all of the Compton wavelengths properties, or the properties that are related to the Compton wavelengths, it's also possible to describe the rest mass energy, which is usually denoted by mc squared, with a lot of other equations that you probably also have never seen. So you can have an electric equation for the rest mass energy, a magnetic one, a rotational one, a gravitational one, and some of them reduced to HFC, to an HF term. And this one reduces to MC squared. And this at least leads to two main conclusions. Energy terms of the form h times frequency are not only applicable to photons, they are really also applicable to particles. I think that's a very important point. And that the mass energy might actually be originate from other forms of energy. So mass in itself might just be, in reality, just be energy, and mass as an independent property maybe does not really exist. Okay, there is also, so we were now talking about the rest mass energy on the previous slide, and now I will talk about relativistic energy, because there are also some unknown things about the relativistic energy. There's also a very different approach to relativistic energy with frequencies. You have to use the de Broglie frequency, which is more sensible in my view than the de Broglie wavelengths. The de Broglie wavelengths goes to infinity if a particle is at standstill, which is quite annoying. If you use the de Broglie frequency, it's simply 0 if a particle is at rest, so it's like conceptually much easier. I've written the equation down here. We can also see that the de Broglie frequency is structurally very similar to the Compton frequency. And it's actually possible to use Planck's constant and the Compton frequency and the de Broglie frequency to calculate the relativistic energy of a particle. So here is like the usual relativistic particle energy equation that you will find in a lot of textbooks. And this one you probably have never seen before. And initially I was thinking that the de Broglie frequency is maybe also related to the rotation of the particle. But when reading the work from John Macken, this is an image from the work of John Macken, as I now tend to think that the de Broglie frequency is actually related to a modulation of the Compton frequency. And since the Compton frequency and the de Broglie frequency both are, I assume, to be intrinsic to the particle, my conclusion is that the relativistic energy of a particle is also intrinsic to the particle. It's not just some magical frame property, whatever, and nobody knows where it's located. It's really like in very concrete form stored inside the particle in terms of some frequency, which in turn means some ether action, whatever. And yet also another implication is that mass should rather be viewed as confined energy than a standalone property. Okay, now we're going from single particles to simple atoms. So we go to hydrogen. So in the simple particle model that I was showing, it also makes sense in the context of hydrogen. So how does hydrogen form? In the model that I was presented, the free hydrogen, the spherical hydrogen, it would expand in size and it would slow down. I was saying that it was rotating with light speed, so it would slow down. It would slow down to a speed that is c times alpha, and it would expand to the hydrogen radius or Bohr radius. And this implies already that the electron is a very malleable thing. So it's not like some hard golf ball. It's really something that has a lot of dynamics, internal dynamics, but it's also deformable. This is what I am currently thinking. But what about the Schrödinger equation? This seems to be completely non-matching with anything on the Schrödinger equation. And I want to put your attention on that term that is part of the Schrödinger equation, 2m divided by h bar squared, which I always found to be a very strange term, because what does h bar squared mean? I have no idea what that should mean. So I was trying to reformulate that term in the context of hydrogen, which is the original context of the Schrödinger equation. And what I came up with is that you can write that term as that term, and this term is a purely electric term. It's just like the electric constant, fundamental charge, so purely electric term. And this leads me to believe that the Schrödinger equation is actually just describing an electric phenomenon. I have also on the next slide, I will talk more about that. And this also leads me to the idea that I think it was unjustified to propose a complete new set of physics based on the Schrödinger equation, is my assumption. And also think there is a fundamental charge squared and the radius of the hydrogen atom here. It is also like very clear why the Schrödinger equation cannot be applied to other atoms like helium, because they will have a different number of charges and a different size. So it makes, just with this simple rearrangement, it makes total sense why you cannot go, cannot use the Schrödinger equation for something else than hydrogen. Maybe I'm saying something wrong. We can talk about it afterwards. Maybe some things are not 100% correct. I'm also not a super expert on everything. And yeah, we were also already talking about the value of the Sommerfeld constant. Alexander was already talking about that. Personally, I still prefer that the Sommerfeld constant is an equilibrium constant that is just there to balance two forces, the electric force and a centripetal force. This is the reason why it has the value it has. I have also on a later slide we will see a similar relationship also. Okay, now it gets interesting. Higher states of hydrogen. So I was already saying that the simple particle model made kind of sense to form hydrogen, but it also makes sense when we're going to higher quantum states of hydrogen, actually. The thing is that here on the right you see the typical textbook probabilistic clouds of quantum mechanics that are usually displayed. But there is an equivalent definition or approach that uses spheres. And the thing is that the probabilities become current densities and current flow on the surface of the sphere. And the approach on the left side is actually producing the same results than this one. But on the right side, it's actually easier to make some calculations. And yeah, if you want to know a good mathematical description of the left side, then you should look up the work of Randall Mills. He already figured out all the mathematics. It might also be not entirely correct, but I think he did a very, very good job. And he calculated binding energies for hundreds of molecules, and you can do that with much less computational effort than is done with quantum mechanics. And he does that to like 6 or 7 digit after decimal point. So this works very, very well. And there's also another very, very interesting thing is that using that approach, it's possible to describe hydrogen states with the electron below the so-called ground state. So that the state n is even smaller than 1. Randall Mills calls these the hydrino, and he's already in the process of making an electric power generator to use the hydrinos to create energy, because the quantum jump from the base level to the first one below, it's like very huge, and it's emitting high energy photons. But you need a catalyst to actually create hydrinos. So they do not appear very easily. You have to have a reactor and have the right catalyst, and then you can make hydrogen to jump one level below. Mills is receiving a lot of hostility. On one hand, that is because Mills is very bold in his claims. So he's saying he has a theory of everything, which I think is not true. But if you step out and say you have a theory of everything, of course, you will have a lot of enemies already. And also the next thing is that modern quantum physics cannot model hydrogen with a state below the ground state. And so should the hadrino really exist, which I tend to believe, then modern quantum physics is screwed. So this is also a reason why they are, of course, pretty hostile to everything he says. And maybe the hadrino might also be responsible for dark matter. Maybe, maybe not. I'm not sure. Mills claims that some of the spectral signatures that can be found in astronomy point to the fact that dark matter might be related to hadrinos. Maybe, maybe not. We will see. But it's definitely a nice idea. So, okay, this is more of a speculation of mine. I cannot say that this is like really substantiated, but I find it interesting to entertain that idea. We were already seeing that the moment of inertia of a spin 1/2 particle seems to be a thin disk. For the photon, it seems that the moment of inertia of the photon is a thin ring. And by extension, a photon should be a toroid, and a toroid with an AC current on top of it. And remarkably, the first indirect image of a photon that was ever made, which you will see here, pretty much looks like a toroid to me. But I have to add, the people who made that image, the creators of that image, they say that it does not have anything to do with the geometrical layout of the photon. So they are just saying it's some kind of energy level visualization, whatever. But I find that to be a pretty interesting coincidence that I think it's a toroid and the image of the photon that I get looks like this. So interesting. Wave-particle duality for the photon should also be explainable. The toroid is responsible for the particle part. And I think also that space is polarizable, and I think that the wave part would then be the effect of the AC current of the toroid on the surrounding space, so that you have both. That we have to consider both the toroid and the effect on the surrounding space, and then you get wave behavior and particle behavior. That would be my interpretation. And also I think that photons and particles have to be made of the same stuff, preferably the ether, to be interchangeable. So how can matter create photons or vice versa if they are not made of the same stuff? So this is also why I'm thinking of the ether is a good thing, trying to explain things in terms of an ether. Okay, then there is also a hidden particle hierarchy that is centering about the Planck sphere. The Planck sphere has a radius of 1 Planck length and a mass of 1 Planck mass. And all spin 1.5 particles are a function of the Planck mass. So this is the equation here. So the proton and the electron, they have this mass formula actually, which is, like I said, a function of the Planck mass. And in reference to what Alexander said earlier, Alexander, this is the formula that you were showing with H, like H equals whatever. It's just written in a different form. This should be exactly the same formula. And so this all leads back to the Compton wavelengths that we started with. The next interesting thing is that there is a kind of mathematical mirror symmetry. So here we have the formula for spin 1.5 particles. And if you look at the formula for most extreme Kerr black holes, these are Kerr black holes that are rotating black holes that are spinning with light speed, which is it's probably not possible, but that's the limit, let's say. They have pretty much the same formula, just the fraction has to be inverted. But there is also another thing by that is not exactly true, because spinning black holes probably bulge. They are not perfect spheres, they bulge, so it also does not hold perfectly. But I think it's still good enough to provide some clues about what's going on in the universe. And then the interesting thing is that the Planck sphere, which I get more about the Planck sphere in later slides, what it really is or means, that the Planck sphere is a spin 1.5 particle as well as a black hole. That's possible because the mass of the Planck sphere is much higher than the mass of the proton and the electron. And this graph also leads to the speculation that the proton and electron may be actually inflated Planck spheres. As I will show on a later slide, I think that Planck spheres are like the substrate of space, and maybe some of them inflated during Big Bang or whatever, and during that inflation they actually created these other particles, and that the inflation process somehow leads to a reduced effective mass. They started out with the Planck mass, but with that inflation process they somehow lost effective mass, maybe. And there's also another big controversy here, is that in the model that I'm talking about, the electron is actually much bigger than the proton. So some people might find that absolutely outrageous, because modern physics says that the electron even might be so small, is extremely small or has no size at all. And here I'm saying the completely opposite, that it is even bigger than a proton. But you already said that the electron might be malleable, like a jelly, on one hand. On the other hand, I think that the electron, when it is accelerated, it is shrinking. My findings suggest that it's not only shrinking in the direction of motion, like special relativity says. I think it's like shrinking in all dimensions. And these two facts then lead to the problem that experimental measurements made of the electron size may be very elusive. So it might be very easy to misinterpret these experiments if you're not aware of what's really going on with the electron. So this is my take on it, that the experimental data may have been misinterpreted because they're going to higher and higher energies. And of course, it's getting smaller and smaller and smaller the higher the energies get. So that might be a reason why that, although it seems outrageous, might actually be physically true. Okay, then the next step is, since the Planck spheres are so small, I think it makes sense that they might be the substrate of space, that this might be the quantum dots of space, or however you want to call them. And that they also that they also have a frequency, which I presume is the inverse Planck time, and that they form a distributed network of clocks in the universe. Because how can we guarantee that time runs equally fast in different parts of the universe, even if you leave general relativity out of the picture? The rate of time could be different in different parts of the universe, and maybe the Planck spheres are like giving like a synchronized clock mechanism across the universe. And as I already said, I think that the individual Planck sphere has a mass of 1 Planck mass, a radius of 1 Planck length. But since I said that the Planck spheres are the substrate of space, there should be no empty space in between. But how do you stack spheres without leaving any empty space? And this is why we would need the octahedrons. I will get deeper into that on the next slide, what that really means. First, I want to add that the Planck spheres maybe also have a charge. They might be the positive or negative Planck charge. That would be a binary. They could just have two different values. That would also be, when we're talking about philosophy, it would be like the manifestation of duality on the Planck sphere level, maybe. Yeah, and you also get the Planck force from the centripetal acceleration that could be associated with the Planck oscillators. Okay, so I go to the next slide. Okay, this slide shows the equations to count the number of Planck oscillators. So the first equation shows you how to count the Planck oscillators on the surface of a sphere with radius r. And the second equation shows you how to count the number of Planck oscillators in the volume of a sphere with radius r. For these equations to be exact, the sphere has to be much larger than an individual Planck oscillator. So That's the limit that is needed. And on the right, we see images that visualize this. So this is how it would look like on the surface. This would be individual oscillators. And this is how it would look like in 3D space. And this is where the octahedrons come into play. Each rect octahedron is actually a Planck oscillator. And I also think that space is flat. I will get more into that later. It also makes sense to assume that since an octahedron is like the perfect embodiment of flat space because it has 3 orthogonal planes. So it makes it also a perfect representative from a philosophical perspective for flat space. And I also have this funny thing with me, which shows how that structure looks in 3D. And it actually gives rise to a lot of geometric complexity because there are tetrahedrons appearing in cube octahedrons and tetrahedrons of all sizes. So this is actually a very, very funny structure. And okay, now you might think, okay, now he's completely lost it. He's gone completely crazy now. But actually, all of this ties into known physics. So, for example, what we're having here is actually also the Bekenstein-Hawking entropy. This is just a visualized form of the Bekenstein-Hawking entropy. And also, this structure here, it also gives you the 0-point energy of space. So if it is real, we don't know for sure. Maybe it does exist, maybe it does not exist. But this structure gives you the same energy for the 0-point energy of space, like 10 to the 96 kilograms per cubic meter. And thank you. And there's also some other very interesting property that arises from that structure. You actually get the acoustic impedance of space for gravitational waves, which is like a very high value, 10 to the 184. And it's this value here. This is the acoustic impedance of space. Usually in the science of gravitational waves, what is usually used is c cubed divided by g. So usually in the literature, it's stated in a similar way, but not the exact same way. But this way has the advantage that these are actually the units that are usually used to describe an acoustic impedance. And this is the equation for the intensity of a planar gravitational wave. And this is the form that is adapted to describing the acoustic impedance with this unit. So you can adapt the equation for the intensity of the gravitational wave. It can be easily adapted, and that is the form. So a lot of things are actually coming together now here. And for friends of the esoteric realm, which not too many of you may be, but the flower of life pattern is actually also encoded here. So some of you may know it. I think it's a nice coincidence. Okay, then we'll switch over to general relativity. The effects that general relativity is predicting can also be achieved in flat space when you move the effects of curved space into the various physical quantities. I start with the example. So we all know that there is gravitational time dilation. But if there is gravitational time dilation, and that is physically real, that energy must also be changing in a gravitational field. What energy means, the gauge for energy also has to change. And if energy changes, or a lot of the other quantities have to change too. So you cannot say time is changing, but all the rest is not, or it's just an imaginary math exercise. That's inconsistent. So if time is really changing physically, then all of the rest has to change physically too. And here in that table, you see the factors that would come out to get the same predictions like the Schwarzschild metric gives. So for time periods and frequency, that's the factors that you would expect, and these are the exact values or the exact factors, and these are in its column to the right, it's like the linear approximations. Energy also scales like frequency. Interestingly, force remains constant. Force does not change. When the row with length element, what length element actually means, it does not mean that space is changing. It actually means that physical objects are changing. The physical objects are changing their size. And I also have to add that a local observer would not be able to detect these changes. This would just be observed by someone from outside. As you go into the gravitational field, you will actually not see that these things are changing, because everything changes in a way so that the change is actually concealed from you. You will not be able to measure it locally as you go into the gravitational field. For you, everything will seem to remain unchanged. And yeah, velocity is also slowing down. And this means in the absence of acceleration. So if something goes in that actually does not feel any acceleration, it would still slow down from the perspective from someone outside of the gravitational field. And with all that knowledge, we also can get an equation for the mass energy of a spin 1/2 particle that incorporates the special relativistic effect as well as the general relativistic effect. This is this equation. This is how the mass energy would change with special relativistic, considering special relativity and general relativity.
Is the length element also different in both directions?
Yeah, I think so. I'm not absolutely sure, but I think it's like a symmetric shrinking. Okay, and yeah, interestingly, acceleration would decrease and mass would increase. Okay, so then tests of general relativity. So something else that I have to add. So this slide this does not constitute a new theory of gravity. It just says if you come up with a new theory of gravity and it can fulfill these factors, it can produce these factors, then you will be equivalent to the Schwarzschild metric. So if you come up with a flow model and your flow model predicts that the quantities change in this way, you will be on par with the Schwarzschild metric and general relativity. Gravitational general relativity tests. There are no surprises with time dilation and gravitational redshift and blue shift. This is pretty straightforward, just change of a rate of time and wavelengths. It gets more interesting with light bending and Shapiro delay. Alexander was already talking about that. So I was saying that velocities are slowing down, and I said that it is even in the absence of any experienced acceleration. And this then also extends to light. So light also has to slow down inside the gravitational field. And if light slows down, you can calculate a refractive index. You can define a refractive index. And you have a refractive index. Light bending can be seen as an optics problem. And as Alexander already said, Robert Dicke was the first one to point that out. So that's just confirming of what others already have found out before. And in my latest paper, I was also trying to tackle the perihelion precession. And it seems that my calculations succeeded. So if you treat the mass of Mercury as a variable mass with the factor that I presented, it seems that you can calculate the correct perihelion precession. I have a printed version of my latest paper with me, so whoever is interested to see the details of that calculation is invited to take a look at it. I have to add, though, that maybe there is still some conceptual issue, so it might not be completely free of flaws or whatever, but the math worked out, and that's, I think, is already a good start.
You have 20 minutes remaining, by the way.
Okay. Okay, that's good. That should work out. Apart from all of the formulas that we have seen that might be pointing to the space being flat, there are also a number of conceptual arguments, in my view, that advocate for a space being flat. Someone already said it, maybe it was Henry, that the Schwarzschild radius already follows from escape speed. You just take the Newtonian escape speed, you say, okay, just add the additional assumption that there is a speed limit, and then you have that equation, and you just rearrange for r, and you have the Schwarzschild radius. So actually Newton was in some way already predicting black holes.
Yes, and people who've modeled flowing space with black holes, they say that it's a flat space.
Yeah. Yeah, yeah. The next thing is that curved space can't push against an object blocked from free fall. So if you have an object and you block it from free fall, then if there really is just curved space, it should not experience a force, because how can curved space push against a blocked object? And if you tell me that curved space is pushing against a blocked object, an object blocked from free fall, then it's again a force, and you were always telling me, no, it is not a force. So like, what's going on? So I think this is like a very good conceptual argument against curved space. Why and how mass bends space? No one knows. G itself is not derived by general relativity theory, as Alexander was already pointing out. Our observable universe seems to be a black hole, or at least close to being one. I will get to that also on one of the next slides. The refractive index n for light indicates that space can be considered to be a medium. Planetary perihelion precession may be explainable by variable mass, and you don't need a curved space for that. Fundamental forces may be explainable by wave phenomena. There is some interesting work from John Macken, and I think Chantal is also going in that direction tomorrow. Time is phenologically and experientially different from space, so why have a combined space-time? Newtonian gravity, the equation for Newtonian gravity, can be obtained from the Schwarzschild, from the black hole horizon of a Schwarzschild black hole. You can check the work of Eric Verlinde. He has shown that. The equivalence principle may not always apply. See the work of Michael McCulloch. I think Alexander knows Michael. Space itself has distinct properties: propagation speed, energy density, that might be the 0-point density we're talking about, and acoustic impedance. Incompatibility of modern quantum physics with general relativity indicates that one or both theories are wrong, or at least, I mean, of course they make correct predictions, but they might, on the physical level, on the explanatory level, descriptive level, they might still be wrong, despite all of the correct predictions they make. The strong force might be the close proximity behavior of gravity, a strong claim, I know. I also have a slide on that. That indicates something in that direction. And Minkowski space may rest upon arbitrary assumptions like constant speed of light, and yeah, there might be some issues with that, and also like the combination of time and space into a combined space-time. So Minkowski space might also have its problems. Gravitational potential energy. So in electromagnetism, the potential energy is stored in the field. So the Poynting vector is related to that. But the same concept does not carry over to gravitational fields. There, the potential energy between two masses is not stored in the field. That doesn't work. And if you ask the question, what actually is gravitational potential energy physically, nowadays you usually get an answer that involves space-time, bent space-time. But there is actually something much more interesting, much more classical explanation. So what you can do is, or I was already talking that the mass energy inside the gravitational field is changing. And what you can do is, if you take the difference between the mass energy at two different positions in the gravitational field and calculate the difference, this is exactly your gravitational potential energy. It's pretty exact. So this is probably the real cause of gravitational potential energy, is like how the mass energy is changing inside a gravitational field. But as I already said, a local observer is not possible to measure these things, because for him things all change in a way that this is concealed from him. And this is why physics accounts for that as the gravitational potential energy, because it's a kind of invisible change for a local observer. There is a very interesting shorthand notation for writing the electric and gravitational force that was introduced by John A. Macan. It's like here. I just have to explain what these terms mean. So we are already saying that this is the Planck force, and A is simply quantifies the Compton radius of a particle in terms of the Planck length, and M simply quantifies a distance r in terms of the Compton wavelengths. These are two measures that are used for the shorthand notation. And curiously, it's possible to write the gravitational force in this form. It's exactly the same as the Newtonian gravity. And you can write the electrostatic force like this. And what's now very, in my view, remarkable about this is that the gravitational force and the electric force, they are pretty similar structurally. There are only two differences. The power of A sub beta is different. Here it's to the power of 1, and here it's to the power of 2. And here we have an additional Sommerfeld constant. To me, it's pretty remarkable to have this similarity, structural similarity for two forces who should not have anything in common. But still, in this notation, they are quite similar. And starting from that, it's also possible to go from here to planar wave equations. This is possible because the Planck force, which is c to the power of 4 divided by g, can also be written as a planar wave equation. And this enables you to go from this to this. And so you have a planar wave equation for gravity and a planar wave equation for the electrostatic force. Admittedly, there are a lot of open questions with these equations, and I don't have all the answers for this. I just find it highly remarkable to be able to get these kinds of equations. And the planar wave equations, that's important to add, they also feature the impedance of space. This term here, it's again the impedance of space. So what we were seeing like for the intensity of gravitational wave, macroscopic gravitational waves, it also might be relevant for the gravitational force and the electric force. And there is again also the Sommerfeld constant appearing in a similar equilibrium situation like I was already talking about in hydrogen. You have another equilibrium situation here, but here it involves the square root of alpha. Okay, black hole universe. So here, this is the size of the observable universe, approximately. And if you assume that the universe is a black hole, and take the black hole mass for that radius, and just divide it by the Cartesian volume of a sphere, what you get is that the observable universe has this density, and this is exactly the critical density of general relativity theory. So if you take the observable universe, say, okay, it's a black hole, divide it just by the ordinary flat space volume, you end up with the same result that general relativity is predicting for flat space. So this is another argument for that our observable universe is a flat space, and that and NASA was also validating that result with its Wilkinson microwave anisotropy probe survey. Complicated name, I think the short one is YMAP, the YMAP survey. It also came to that conclusion or to that value. And this suggests that, as I said, the observable universe might be a non-rotating black hole, or at least it is close to being one. The space of a universe is overall flat and has no central singularity. And I also think something else that leads to is that the gravitational constant G is an emergent quantity, which means it follows from other properties, like Alexander was also talking about. I think my equation is a little bit different from Alexander's. I think that this equation is correct or accurate in case the universe is isotropic on large scales, which might not be true. I think this is still debated if the universe is really isotropic or not. But if it is, then this equation should be correct. Something else that follows is that if our observable universe is a black hole, and black holes are generally the most dense form of matter, then what also follows from that the limit for our gravitational potential in our universe is minus c squared. This is also something that Alexander was already touching on, because the units of velocity squared and a gravitational potential are the same. How much time do I have left?
Yeah, just 8 minutes left.
Okay, so maybe I leave out that. So this is how you can reformulate the gravitational potential. It's like you can replace G with c squared, and you get very, very interesting equations. Force relations. So this slide is about the Planck force, which Salvatore Pais, some of you may know him. He's a US Navy researcher who has some crazy patents which are public, which read like UFO technology. So really some very crazy stuff, but patents available. He also calls the Planck force the super force. And it's called super because it's probably the strongest force possible. So you need a black hole to achieve that level of force. It presumably is the first force in the universe that ever existed. On the level of the quantum from the Planck spheres that I was talking about, it might still be relevant. And I think that the other forces in our universe in some way descended from the Planck force. So the Planck force was the first one, and as the universe evolved, it started to create these other forces. And if you start to rewrite the usual equations in terms of the Planck force, you get these equations that you probably have never seen before. It gives absolutely the same results like your ordinary equations. But these equations have the advantage that it's much more easy to see the relative strengths between the different forces. And I have to add something here. Why I'm writing here the strong force with that formula? That seems a bit weird. The point is that if you calculate the force for the proton radius with that equation, you approximately get the strength of the strong force. So surprisingly, this lands you in the right ballpark if you calculate the strong force. So therefore, I call it an approximation of the strong force. And then the next thing that happens is, okay, from that force to that force, you just have to add an alpha and you are arriving at the electric force. And then from the electric force to the magnetic force, you just have to add this velocity components on the back side. I think this is one of the most beautiful equations for magnetic force, but it's for a special case when the electrons are, or the charge carriers are in parallel or antiparallel. Then it actually simplifies to this equation. And this is how the gravitational equation, how gravity looks like if you express it in Planck units. The appropriate normalization value that you need for the masses is the Planck mass. But there is also a second very interesting formulation that I had to add. It's like this one. We were already talking about the flow model, and this is Newtonian gravity expressed in terms of escape speed. So here is the escape speed 1 and escape speed 2, and you have to divide that by c squared and square it again, multiplied with the Planck length, and also this factor here. And this gives exactly the same prediction like Newtonian gravity, despite being very, very different. And there's also something very interesting about this factor 1/4. This is because Newtonian gravity is dealing with static objects and not with rotating objects. This is like we have 2 times a factor of 1/2 that is missing from the escape speed formula, and this is why we end up with a factor of 1/4 here.
Martin, I have a question here. Now, in your the table, the formula for the strong force and the electric force is proportional. So, now how can you account for the fact that electric force is a long range force, but the strong force is a very short range force?
Yeah.
So from this formula, I cannot tell the difference.
This is.
Can you elaborate on that?
Yeah. This is why I call it an approximation, and I think it should only be regarded at the point at the size of the proton. It is not a universally valid equation, but I think it has some validity to it, but it's not an accurate something that can really be used for the strong force. But at the radius of the proton, you pretty much get the strength of the strong force. And that's also one of the mysteries to uncover. It also has another side effect or another variant. This is the gravitational formula for 2 protons, the gravitational attraction between them. But if you assume that you could replace the mass of the proton with the mass of the Planck mass, that the real mass would be the Planck mass instead of the measured proton mass, you get a force that is 10 times to the power of 38 stronger than the usual gravitational force. And this is pretty much by what everyone is saying, that the strong force is stronger than gravity. So I think this is a hint that there may be like that the actual mass of the proton might be even bigger than we know. So it might be like the mass that we measure is somehow shielding the real mass. But this is getting more into speculation. But I still think that arriving at that ratio, I think, is pretty interesting, and there definitely needs to be an explanation of why this is the case. Okay, and this is the last slide. In our universe, there seem to be a lot of interesting logarithmic relations that end up either in an integer or approximately end up in an integer value or integer value plus 1/2. There are a lot of logarithmic relations between mass of the electron, mass of the proton, Planck mass, Compton wavelength of the electron, and they all end up in either an integer number or an integer number plus 1/2. It's like very weird, and it indicates there is some unknown physics at work, maybe like standing gravitational waves or something like this. Okay, and that's it. Thank you for listening. Andy.
Amazing stuff, and it correlates with a lot of theories I have come up with, like, I think the flow is due to the strong force, is a strong force phenomenon. But one question, you have this Planck mass. How can space have mass? How could other things move through space if they're hitting a Planck mass, which would stop them cold if their mass is much lower?
Okay, on one
Is
hand,
it really mass that you're talking about?
yeah, I think it's more like energy. It's just mass energy. It's not. It's because I think it's something that is in some way vibrating in some way. But not really. Mass is just another way. Or, like I said,
Mass energy.
Mass energy is actually
Yeah.
the real thing. And this means that something is vibrating in some form.
Yes. There is some internal
Oscillation, vibration.
motion.
Yeah, there is something going on, and it can be expressed as mass, but it really is some kind of energy, some kind of wavy action or oscillatory action is going on.
I think that the spin half is more fundamental in structures than spin one. What do you think?
I have not delved into that. I cannot give a good answer to that.
Thank you. Just for very, very short remarks. In terms of electron clouds, again, thank you for restoring my sanity. There are endless examples in biological chemistry where you cannot really, it's impossible to think about electrons as point charges moving at probably FTL speeds and still be able, without them having different shapes, you cannot really explain lots of biochemical reactions.
Yeah.
You cannot explain the shape of the DNA. You cannot explain why, what happens when the stuff from the smoke, the tobacco smoke, intercalates into between the base pairs. So if you want examples, real life examples, including electron atomic force microscopy, there are on this topic there are tons. We can find them easily. On the particle hierarchy slide, there is one thing I am missing there is that black holes have three actual parameters: the mass, the rotation, and the charge. So I was wondering what would happen if you had the third axis for the charge. How would the planes look like? Because obviously the proton and electron would not be on the same line anymore. They would be on the completely opposite sides of the charge axis.
Yeah.
So perhaps that would help. Really interesting to you.
I'm also not. I'm actually not sure about our charge. I wonder if black holes maybe are mandatory to be neutral. I'm not sure. I'm not sure if you have any observations on the charge of black holes.
I mean, it's impossible to say at the astronomical scales, but in principle they should be. So, just a thought.
Yeah.
I don't want to hog too much time. Geometry about the geometry of your atoms of space. I too have been trying to solve this because I'm interested in the river model, but from the bottom up. So I'm trying to find out what would be a fluid which has quote unquote molecules which allow zero viscosity flow. This is not obvious at all how to do that. And what you have here is very interesting to me because it looks like a zero energy limit of what I've been doing. So I think there is a very easy way to marry the river model with this. And finally, observable universe not non-rotating. There are where I've seen some a little bit more speculative work, wondering if it is true that it is non-rotating, or because perhaps it is, and it can
Actually, the overall universe might be rotating. So there is also a difference between the observable one and the full universe. So maybe the full one is rotating, but the observable one, that's like so little that we actually don't detect
so I
it.
was wondering if you have your comments on this, if you see this works.
Yeah, the overall universe might be rotating, maybe. And there has been some recent discussion about spin of galaxies and if that indicates that the universe is rotating. Okay, Mr. Chang?
Yeah, I agree with you that it's not a good idea to use the curving space-time to explain gravity. And you list a number of reasons, which is very, very helpful, okay? But to me, I think the overwhelming reason against that idea probably is, I hope someone can address that to me, there's no physical mechanism to explain why the presence of a mass will curve the space-time. This bothers me a lot, okay?
how and why.
This is
Yeah.
really overwhelming reason. So I don't know whether anyone, over here will have any explanation for that.
But I can maybe give you an account of like why people came to this. I mean, initially, people started questioning whether we might
Can you speak a little bit louder? Sorry, because my hearing is
people
very
started
bad.
questioning whether we might be in a non-Euclidean space, and they wanted to determine this experimentally. And so they decided that we would determine the geometry of space by measuring how light curves, for example, or something like this.
Are you talking about the accident experiment of the light diffraction? Or what?
No, just
asking,
speculations in the late 19th century. And then what happened is, what Einstein was doing when he's referring to curved space is just defining space's geometry in terms of the behaviors of solids and rays of light.
I think before time.
I know he
Can we ask questions?
Yeah, next one.
Yeah.
Yeah, I think Jan had also a question.
More a remark than a question. So you didn't mention Dirac's large numbers explicitly, but they are baked very deeply into the equations that you showed, for example, where you related the electrical and gravitational.
Yeah, I've also done playing around with that a little bit in a paper of mine, but I've excluded it from the presentation.
You seem to be interested in the same coincidences as Alexander, just phrasing them very differently.
Yeah, coming from a different angle, maybe you're adding something. I've read Alexander's books and videos, so I'm very inspired by what he is doing.
Yeah, a brief comment here. Well, thank you very much for pointing out that you believe the strong force to be explained by gravity, short-range gravity. Absolutely in agreement with that. And I mean, even if modern physics would ridicule maybe that thought, don't be ashamed. I mean, Einstein or Heisenberg would totally be in agreement with you. That is one thing. And second thing, also, thanks that you added this. We don't have to worry about things like closed universe or inflation. Once you calculate the gravitational constant, that's already baked in. That being said, you mentioned, you talked about black holes. And they're kind of strange by construction because the density you would expect normally I mean, the mass you would expect normally to vary to the third power of the radius. It's just linear, which is very strange. And as a consequence, a swimming pool of the size of the solar system, say, would be a black hole. So it contradicts somehow this idea of a very huge density. Are you skeptical of the concept of black hole as a whole, or?
Okay, I assume that they are real and that the equations are quite correct, but I might be wrong. This is just like my best guesses, let's say. I'm not saying, or I cannot say that that's really correct or true. It's just like what I try to how I try to make sense of things. So might be that they don't exist. I think they do, but we will see.
A brief comment. I found about a third of this vaguely plausible and interesting, but what would give this real power is direct reasoning from specific evidence, specific reasoning steps, getting to definite conclusions. Anything and any of these bits that you've shown us here that could be directly proven would be powerful.
I think it was you that already said that some of the greatest minds failed to do that, right? So I think it's actually not that easy. So
no, it's not easy, but it would give us a lot more power.
Yeah. So like I said, it's mostly a collection of clues. Like I said in the beginning, I don't have a full-fledged outer theory. It's just like all the noteworthy things that it was coming across, and I tried to stick it together in the best way that I could. So maybe some of you have found some things where he can start building out or integrating in his own stuff. So then a lot would have been won today. So.
Sorry. when you talk, it's interesting, you talk about the possible structure of the space. Now, when you look at the question, so a natural thing must come to your mind is that what is the material that make up this structure? What could be the physical property of this such a material that make up the structure of space?
Again, can someone help me with the question?
Yeah, what could be the physical properties of this stuff that makes up this spatial structure you're talking about? Like what properties does it have, is this question.
Yeah, this is the properties of the Planck sphere that I was assuming, but this is, of course, just a best guess or trying to... I just thought it makes sense to use the Planck sphere because it was kind of this symmetry point or center point, and that it makes like a good candidate for what might be the most basic structure of the universe. Yeah, the substrate.
Are they light rays and structure through the energy flows everywhere?
So I think this will also be an elastic solid. So Chantal is talking tomorrow. I think this can also be interpreted as an elastic solid, and Chantal will talk about this tomorrow. So
Maybe we can discuss that. Yeah. Try. I just see if we have any similar idea, so we can compare notes.
yeah. So there might be some connection. Yeah. All right.
Yeah, wonderful.
Thank you very much.